the original iteration method, Mathematica. And what I want to start doing with these are our initial parameters that set up our system. This is the lattice constant. This is how many points actually here. I'm gonna add something. This is how many points are gonna go in each direction. And I'll call it n max. And here I'm gonna change this to n max. And the last one is gonna be n max. Now the big change I want to do is instead of 100, let's just do 11 so I can see the squares in my lattice. I put it there. This is the value now, 11. And the first step is that we're gonna generate the potential phi is gonna be a matrix phi here. Phi is a matrix that is generated with a value of 0.5 everywhere, and it goes from init, which is 1, to last, which is 11, in values of 1 in both the I and j direction, in this case the x and y. So by initializing it, we have it here. It's all blue because blue is the value of 0.5. Then what I want to do is fix the top to 1. In this case, the top means that we're going to be working with the first row. That would be the top. And we have fixed it. Every element from 1 plus 1, 2 to 10, because we didn't do the last one, is initialized to 1. Here's it is. These are all to 1. These are all to 0.5. We do the same to the bottom, and here the only thing that we change is that we're in the last row, and our last row is there for 1/2, 1, 1, 1, 1, 1, 1, 1, 1, 1, all the way to 1/2. Then we want to fix the 0, the left and right to 0, and we start by changing for every value in the first column. We're gonna go from 1 to last plus 1 when I is less than last plus 1 is gonna be doing this. So that means that when I reaches 11, it's still less than 12, so it keeps going, does all of this stuff in the loop, and then that gets added one more value. This extra value makes I 12, and then 12 is bigger than 11, so we're done. So we're doing the first loop is gonna change the things on the first column, and then the second loop right here is gonna change things for the last column. And then we're just plotting it. So in this, we get the square, 0 everywhere here, 1 up here, 0 everywhere here, 1 right here, and then we have 1/2 all the way in the middle. Now I'm gonna set the values in the corners to 1/2 and then plot it again. So now we change this value, this value, this value, and this value. This is where our boundary conditions are set. You can look at what the array, the values inside of the phi array are, and you can see that the 1, 1 is 1/2, the 1, 2 is 1, the 2, 1 is 0. So that would be the 1, 1, the 1, 2, and the 2, 1. Those three values are the first one there. This function right here, it's updating. The updated value is the average of the 4 nearest neighbors. So we have that. And then we also update here the sum. So the sum is updating, is grabbing the values of phi everywhere, and it's a sum of this expression which was given in the lecture. So in this case, if we do the sum, this sum right here is the first sum. So if I look at sum, the sum of this quantity over all of the values that we're going for goes to 10. So then here I want this value to be sum of S1, which is calculated again and is stored in something that we call list. This is a vector. And this is just to look at what the update function is doing. So if we wanted to update the second row 9th value, we would do this by hand, and we can do it here. And that's just changing the value of phi in the second row 9th column to the value that it should get from averaging around its neighbors for it and then plotting it. So there we go, we changed this value right here. So this is the new value for this column, for this 2, 1 right here. So it's not 1/2, as you can see, it turned a 10th bluer. And if we were to plot it, we see that this guy is 1 is blue, 0.5 is the yellowish, and 0.625 is the tint a little bit bluer that is here. All right, so then if we look at it, by changing that value, just one value, we reduce the value of sum from 10 to 0.9 to 9.9375. This is just to have the two values together. All right, so this region here for the for loop, what it's doing is that it's going to do this 999 times. So we're going to be doing this where we update every value of phi going from I is equal to 2 from the row column setup from the second row all the way to the 1 minus the last one. And J is going from the row, so it's going from left to right and up and down. And then we're also going to be looking at this being updated, this S sum being updated. We do it 1,000 times. This is not going to take too long because it's done for only 11 by 11 box, but now we have the results right here. And in matrix form, we see what it looks like. There's a region that is 0 because it never changed in those values. So actually during our for loop, we didn't update this, and this because those were our boundary conditions. And all of the values in the inside were updated until the relaxation was done. And that's what we see here, that the relaxation was done probably after 2 or 3 parameters here. 2 or 3 values of the loop. So we can look at the potential and plot it here again. And here is just plotting whatever the value of phi is. And we have it again here. And then here I have a manipulate, and I'm plotting and manipulating so that I can change the values of my J here and here. So let's look at that second plot, and it's this one here. I'm expanding the two, and this is looking, the first one is going from 1/2 to 1, 1, 1, 1, 1 all the way across to again 1/2. So if I go and change, this is this one up here, right? So you're going from 1/2 all the way across to 1. So if I change from the first one to the next one, this is the second row, third row, fourth row, fifth row, sixth row, seventh row, 8, 9, 10, 11th row. So we were going at the 10th row, it was 0, and then these values in between. And then the 11th row, it was these values across like this, where it's again 1/2, 1, 1, 1, 1, 1, 1, 1. As shown here. So this one is 0, and then this value right here is 1/2, so it's 0, 1/2, and then it goes all the way to 0.8 and comes back down to 0. And if we do the same for the other side, we're cutting across here. So that would be going across in this direction. This is the 11th row, so the first value is at 1/2. Sorry, yeah, 1/2 is this one up here, and then the last value is at 1/2, but in between is 0. So therefore it looks like this, but as we start moving forward, we see that it decreases. So let's put it here, and let's put it here. So that would be the yellow line is going across here, 6 value, from 1 to 1/2 back to 1. And then the blue line is going across from 0 to 1/2 back to 0. All right. So now those are the plots that you have to generate. And then the other aspect of this is then to grab your boundary conditions and change them. So let's do the first example. So we start again. Everything here is at 11. Then everything is going to be started at 0.5. That's just your initial value. And this is where it gets important. Let's say that the top end, we wanted it at 1. But we wanted to change the bottom end to 0. This is where we change that. Right here is the last row is going to have a value of 0 in between those two values. And now we're going to add these guys to 0 and the other side to 0. So now we have all of this to 0. We still have to deal with the corners. So we want the first corner to be at the average between those two guys. So this one should be at 0.5. So that's perfect. This is the other corner, first row, last column is this one. We also that one to be the average of these two. So that one's set at 1/2. Then we want this one to be 0 because it's the average of this value, and this value should give you 0. And the same for this too. So we do that, and that's our boundary conditions. And now our code is going to go and figure out what is the potential along this area. So let's go back here. This is already done, so we don't have to redo it, but this one we haven't. So we can redo it here. And that's now 9.75. And let's update this one. So this one didn't change because it's the average of the 4 values around it. So that didn't change. But if we had done it over here, it would have been different. So let's do our operation 1,000 times. We start doing it. It takes a couple of seconds, but Mathematica is done. This area remains at 0. And now this area is the only one that changed from before. You can compare that to the previous approach. Let's see. Compare it to this one down here. So let's plot the same potential again. And now let's look at the cut in this direction and in this direction. So we have the cut that goes from six through 6. So let's look at that one. So we want the one that goes through 6. There it is. It goes from 0 to 0 and it reaches around 0.25. So that would be this cut through here. And then we look at the cut that goes from 6 also. And that one goes around like this. So this figure right here is the one that goes from here at 1 and then decays all the way to 0 here. These are the two ends that were fixed. This one is fixed at 1. This one down here is fixed at 0. But the values in between were relaxed there. All right, so one more relaxation that you would have to do is the one where you have 1 at 0. So let's do that. No, 1 at 1 and the other one at -1. So let's keep this one at 1. And now let's put this one at -1. Once you have that, then you add the values in between for the two sides. There we go. And now you just have to fix the four corners. So these two are going to be 0 and 1, 1/2. And then these two right here are going to be 0 and -1, -1/2. So we have the 0 and half, half. Then this one should be -5. And this one should be -5. We look at it and it goes like that. So this one is -1, -1/2, 0, all the way to 0, 1/2, and 1 all across up to here, and it's the same on this end. Let's look at the sum. The sum is now 28. And let's do the whole, let's just look at updating this one. So again, just updating this one didn't change anything because here everything was the same. It just changed this guy and it didn't change from our previous experiment. So now let's do our counting for let's do our loop over 1,000 times. And here is the value that we get. And finally, so it took a little bit longer for it to stop changing. So you can see that here is still changing, and around here it's not changing anymore. So it took this many iterations to go all the way to being relaxed. Once you increase n to 101 instead of 11, you're gonna see that this takes a while longer. So let me erase this one. All right, and then we can plot the potential, same as before. It looks now like this, and we wanna do a cut through here. Let's look at that one. So right now it's going from 1/2 to 1 because it's in the first row. So we have this one, and I start changing that 1, 2, 3, 4, 5 all the way to 6. For the blue line, we would get, there we go. So it's close to 0. And then if we keep going, we get all the way to 11, which goes from -1/2, -1 to 1. And there you have it. And let's go backwards to through the middle, although it's the one that has the less value. And now we're gonna do the cut through 6 here. So this is right through the middle, and it looks like this. It's not a perfect line, but it's close enough. So let's redo this, but now changing the number of points to 101. Before it was 100, but I just realized that if you put it at 100, you don't go exactly through 0, so you want to change that to 101. So now we have 101 here. We don't have to change anything here. It's just getting every value to 0.5. We're going to change the value of the first row to 1. There you go, that's the first row. We're going to change the value of the last row to -1. There you go, there's your last row. Then you're going to fix the two sides. Everything in there is fixed. And now we just look at the half values, and the four corners are at the right values. Let's just go down to look at what the value of the sum is. Our sum right now is 298. And let's just do the whole counter, the whole loop over everything. So this one is going to take a while because now you have 101 by 101 elements. So that's about 10,000. And this is one of the reasons that Mathematica is not as good, because it's going to take so long, while Python does this in seconds or milliseconds. So actually, since it's taking so long, I'm just gonna abort the evaluation. I don't know how far it was, but there you see it. It's not done because it should go all the way down. But we can plot it here and then just look at how these guys look as we increase the value. So we want to do it around 50 or 51, and this one too. So it wasn't relaxed completely, as you can see, because this just decays super fast down here, so it wasn't really done. It was like halfway done. So there you have it. The most important stuff to do is just make sure that you start debugging with nmax being a small number such as 11, and you change your boundary conditions here up and down, and adding extra values here. You're adding extra values here. And then if you do that, there's different ways to do it, of course, but what you want to do is when you're updating, if for instance you wanted to update over everything except for this corner right here, then you would have to change either the way that you're updating here so it doesn't go over the whole thing. So here is going from the second to the one before the last, and exactly the same thing here. Or after you update once, then you copy and paste the boundary condition. So if that it updated all of these guys, but then you tell it like, wait, go back and put these values for this corner right here. And you would do that right here inside this for loop, somewhere around here. So you would just go add some values here, and that should make it work. All right, let me know if you have questions.